The cross product. Many physics, engineering, and geometry applications involve finding a vector in space that is orthogonal to two other vectors. So, if we had C, a vector orthogonal to both A and B, what is A dot C? Well, we know to be orthogonal, the dot product would equal 0. So what about B dot C? Well, that would also need to equal 0 because it needs to be orthogonal to both vectors. So let's use this fact, and we would write out the dot product, and it needs to equal 0 if we did A dot C or B dot C. Now let's go ahead and multiply the top equation by B sub 3 and the bottom equation by A sub 3, and the reason we're going to do that is because we're going to subtract the two equations, and when we do that then these will cancel and we will have this one minus this one, so here this is, and then this one minus this one, so here that is, equals 0. Now we're going to take that and we're going to factor C1 out of the first two terms and C2 out of the second two terms. And then one of the ways these would be equal is if C1 equaled this and if C2 equaled that. So let's go ahead and write that down. If C1 equaled A cubed B2 minus A2 B3 and C2 equaled this quantity right here. Now if we took those and we substituted those back in up in one of these two equations for C1 and C2, it's a lot of just algebra, but we could find C3, and this is what we find that C3 equals. So let's take these three components for this vector that's orthogonal to both A and B, and they would look like this. So this resulting vector that is perpendicular to both A and B is called the cross product of A and B, and it is denoted as A cross B. We take these two vectors and cross them, we get a third vector, and this is how it is defined, and it is orthogonal to both A and B. So here is an illustration. We had A and B and we crossed them and we got this vector C. It is perpendicular to A and it's also perpendicular to B. So this is called the cross product. So we have these two vectors, and when we cross them we get this vector with these components that we just came up with by knowing that the dot products between A and C and B and C had to be 0. And this is also called the vector product because we are doing a product, but this time we are getting a vector, not a scalar. And by the way, the dot product was defined for any number of components in a vector, but this cross product is only defined for three-dimensional vectors. Now, as we look at this, that is going to be somewhat hard to remember, and so we're going to actually express this differently. Let's take, first of all, and put this in IJK notation. And let's look for a minute at a determinant. If we had a determinant and across the first row we put I, J, and K, and then we put A sub 1, 2, and 3 and B sub 1, 2, and 3, if we computed this determinant by expanding by cofactors, we would take this first element I multiplied by the determinant of what's left when we cross off I's row and column, so it would be the determinant of this piece. Well, that would be A2B3 minus A3B2. Oh, look at this, A2B3 minus A3B2. Then if we moved over to the second element, remember at the second element this was a plus and this was a minus, this was a plus, so we would need to do the negative of this, but if we cross off J's row and column, we have A1B3, but with the negative on it, minus A3B1, but the negative and negative make it positive, so there it is. And finally, if we moved over to the K and we crossed off the K's row and column and we found the determinant of this piece, it would be A1B2 minus A2B1. So this is the cross product when we expand this determinant by cofactors. So this is a way we're going to be able to remember this formula for computing the cross product. Now when we do the cross product of two vectors, we get a third vector that is orthogonal to each of the other two, but which direction does it go? And so we use what is called the right hand rule for this, and so we take our fingers and we sweep from A to B with our right hand, and the direction our thumb points is the direction of A cross B, so that it would be up. Now if we did B cross A, we would have to sweep our fingers from B to A, and our thumb would be pointing down, and so B cross A would be going down, and we see that that is just the negative of A cross V. It's the same vector except in the opposite direction. So using this right hand rule, we'd be able to determine which way that orthogonal vector would point. So we know the direction of A cross B, but how do we find its length? So if we wanted to take this and compute the magnitude, let's go ahead and compute. We're going to actually compute this cross product's magnitude squared. So that is going to be taking the first component squared plus the second component squared plus the third. So let's write that out. So this would be A2 B3 minus A3 B2 squared plus A3 B1 minus A1 B3 squared plus A1 B2 minus A2 B1 squared. Okay, let's go ahead and expand this. So this would be A2 squared B3 squared, and the middle terms we'd have negative 2 A2 A3 B2 B3, and then the last would be plus A3 squared B2 squared. Continuing, this would be plus A sub 3 squared B1 squared minus 2 A1 A3 B1 B3 plus A1 squared B3 squared, and then the last piece plus A1 squared B2 squared minus 2 A1 A2 B1 B2 plus A2 squared B1 squared. Let's look at all this a minute and see what we could do to express this differently. We're going to pull a little trick here. We have an A1 squared multiplied by a B3 squared, and we have an A1 squared multiplied by a B2 squared. I'm going to add on an A1 squared multiplied by a B1 squared, and of course I can't just stick it on there unless I compensate for it, so I'm going to do that. And then I'm going to actually do the same thing with the A2 squared. Here it is times a B sub 3 squared, and here it is times a B sub 1 squared, so I'm going to add on times a B sub 2 squared, and I'm also going to subtract that off. I'm going to do the same thing with the A sub 3. I have the A sub 3 squared with the B sub 2 squared, and I have the A sub 3 squared with the B sub 1 squared, so I'm going to add on an A sub 3 squared and a B sub 3 squared, and I'm going to subtract it off. Now, why I am doing all that is because now if I round up all of these squared terms, A sub 1 squared plus A sub 2 squared plus A sub 3 squared multiplied by B sub 1 squared plus B sub 2 squared plus B sub 3 squared. If I did this A sub 1 squared to this one, then to this one, then to this one, that would be this term, and this term, and this term. And then if I did the A sub 2 squared to each of the B's, that would be, there it is to the B sub 3, and here it is for B sub 1, and here it is for B sub 2. And then if I did the A sub 3 to each of the B's, there it is to the B sub 2, there it is to the B sub 1, and there it is to the B sub 3. Now the remaining pieces here that we have all have negative signs on them, so I'm going to subtract off a negative. This will actually factor into a perfect square having these middle terms. So we have a sub 1, b sub 1 plus a sub 2, b sub 2 plus a sub 3, b sub 3 squared. Not something that you would necessarily have seen to do, but it should make sense to you that you could follow what has gone on. Now, this is nothing more than the magnitude of vector A squared, and this one is the magnitude of vector B squared, and then minus, this is the dot product of A and B. So this is A dot B, but it is also squared. Now where did we start and where did we end up? Well, we started up here with the magnitude of A cross B squared, and we ended up down here with the magnitude of A squared, magnitude of B squared minus A dot B squared. Now we're going to actually replace that A dot B squared with the definition of the dot product that we found. That was, let's go ahead and replace that, it was magnitude of A, magnitude of B, cosine theta, but we need to square everything. Now we actually then could factor out the magnitude of A squared, magnitude of B squared. So we have magnitude of A squared, magnitude of B squared, and then 1 minus cosine squared theta. Now we could replace this then with sine squared theta, and then we'd have magnitude of A squared, magnitude of B squared, and what we started out with was the magnitude of A cross B squared. We could now square root both sides of this to get rid of the squared, and one thing we'd have to be careful about here is, do we need the plus minus? But we are going to restrict this to values between 0 and pi, and so the sign is always positive there, so we can get by without that. So we would take these off, and we have that the magnitude of the cross product then is the magnitude of A, magnitude of B multiplied by the sine of the angle between them. So the magnitude of the cross product is magnitude of A, magnitude of B, sine of the angle between the vectors. Well, what would the cross product be if the vectors were parallel? If the vectors were parallel, then the angle between them would either have to be 0 or pi. And if we put in 0, we would get 0. If we put in sine of pi, we would also get 0. So the answer to the cross product, if the vectors are parallel, is the cross product would equal 0. So we have this statement, it goes both directions. If the vectors are parallel, then their cross product is 0. If cross product is 0, then we know the vectors are parallel.